All right, so thank you everyone for joining us today on our ASP Micro Nano seminar series. So today I think we have Jonathan Hopkins from UCLA. He's going to be talking a little bit about his work on precision compliant intelligent systems. So I'll let you take it away, John.
Okay, awesome. Thanks, Mike, and thanks for this opportunity. So, like Mike said, I'm talking about precision compliant mechano-intelligent systems. And loosely defined, those are systems that use elastic deformation within mechanical structures to do something that could be characterized as intelligent, meaning learning, computing, sensing, control, that sort of thing. Specifically, I'll be talking about three areas my group has pursued in advancing these types of systems, as you see in the bolded points here. I'm going to start by giving an introduction to mechanical computation to provide some context, a backdrop to help make a case for these systems. So, interestingly enough, humans began pursuing computation with the desire to predict astronomical events. So they began pursuing astronomical kind of calculators. Arguably, the first sort of computing thing was Stonehenge. And of course, these initial attempts at computation were purely mechanical, physical based. There was no knowledge of electricity back then. Planispheres, astrolabes came. Very simple devices. One, if you've ever heard of the Antikythera, this was found near Greece and was vastly superior to anything in its time. It never repeated since. It was like 2,000 years ahead of its technology. But the Earth, most of time, was just all over the nations were just doing simple counting things like chords, stripes on sticks, pebbles, that sort of thing. Abacus did come a little earlier for computation, but really calculation didn't begin to surge till the 1600s with the proportional compass, followed by Napier bones, slide rule. And these are all analog mechanical kind of computation approaches. Calculators didn't come till Pascal's wheel, as calculators as we know them. Then Leibniz, he did a stepped drum calculator, but it wasn't until the arithmometer in the early 1800s that they had commercial calculators. And as around that time, there was a big milestone in computation. This is when Charles Babbage came along and proposed his difference in analytical engine. And if he had been successful building this would have been the first computer, purely mechanical. It can do anything that today's modern computers can do, obviously much slower. But he never finished building this in his day. So unfortunately, it wasn't the first computer. But he inspired a lot of people. Shortly after came devices to perform Fourier transforms or perform differentiation, integration, various things through purely mechanical means. But then people started realizing, hey, we could use electricity to do some computation. Vacuum tubes were born around this time. And then Howard Aiken at Harvard did the Harvard Mark I computer. And that was a kind of a hybrid electrical mechanical computer inspired by Charles Babbage work. And that was really the first computer. And shortly after, transistors were invented. And then they got smaller and smaller. And in came the digital age, and the rest was history. So much that many people today don't even realize that computation was ever done by mechanical means before. They can't imagine how that could be done. So the question is, now we're here in 2026 of what comes next. Is there ever a reason to go back and do computation with mechanical means? And the answer is yes. If you want computation without power batteries for certain applications, or just for enabling any computation, sensing, or control in harsh environments that are not conducive to electronics. So they would destroy electronics. For instance, hot, humid, corrosive mediums. If you go to Venus, rovers don't last more than 30 minutes after all that cost to get them there, given the harsh conditions. Moon dust can mess things up, sharp, jagged, and cause electrostatic issues. Nuclear reactors or nuclear disaster areas. Solar flares, EMP bombs, lightning strikes can knock out electrical systems. Large magnetic fields can be bad. There's things called single event upsets where high energy cosmic rays can actually flip the bit of transistors and from 0 to 1 or vice versa. And that can cause planes to crash and systems to fail. seemingly randomly, and mechanical systems would be impervious to that. It would also be good for extreme temperature fluctuations and the radiation in space, for space travel, floods, vibrations, that sort of thing. What's more is mechanical computation is impervious to hacking and malware. You can't upload a virus to these systems, obviously. They don't emit electromagnetic signatures for secretive operations, and they can be more robust in many ways than electrical systems. It would be a major bummer if lightning struck and set off an atomic bomb, inadvertently. So it'd be nice to have mechanical fail safes to trigger trigger these systems. So what's more is there are many stimuli responsive materials that are more conducive to interacting with mechanical systems. So stimuli like light, pressure, vibrations, temperature, humidity. You can read the rest. And there's many more that could be harnessed to interact with mechanical systems more easily. And mechanical systems can be made biodegradable much more with greater ease than electronics and that sort of thing. So there's a great case for mechanical systems. If they're so great, then the question is, well, why don't we, for these niche applications, harsh environments or power freezing, why don't we just go back to the work that came before the digital revolution with electronics? And the answer is these older systems, they were made with rigid mechanisms like gears, cams, pulleys, levers, things that interact with sliding, rolling, or contact joints. And so as a result, you get a lot inherently backlash and slop that lowers the accuracy of these machines, and they inherently touch and rub. So they have friction hysteresis, which we all know about precision in this community, destroys precision and repeatability. And that makes, that's one of the main reasons these things were abandoned, is that they didn't have the repeatability and accuracy to compute well. They have poor resolution. They can be heavy, clunky, noisy. They produce wear and particulates. They can be dangerous. Clothing can get sucked in them, hair, that kind of thing. They need lubrication, which sometimes isn't conducive of harsh environments. And then it's very difficult to make these things small. So they're big and clunky. Imagine making thousands of these little gears on a tiny scale and assembling them. That would be very difficult to impossible. And even if you could, at small scales, intermolecular forces begin dominating over inertial forces. And so sometimes the physics just stops working. They can jam and they won't even work. And so they fundamentally need to be made large, which gives you low computational densities, and they're very slow computing. So there really needs to be a revolution if we're going to go back to mechanical computation for these harsh environment applications to make these things work. And the new revolution, the vision is to use a compliant mechanism approach where you achieve relative motions through elastic deformation. By doing so, you completely eliminate backlash and slop. You can achieve sub-nanometer resolution and repeatability, which is critical for computing accurately and repeatably. They're lightweight and silent. They avoid wear, particulate jamming. They're soft and human safe, don't require lubrication, and possibly most importantly, they can be additively fabricated at tiny scales, and then they can be pyrolyzed or calcinated so you can burn away the polymer, and useful materials can be left behind, like ceramics that are not susceptible to creep. Stress relaxation are actually pretty good flexure materials that are very robust. They can withstand thousands of degrees, which is what they're pyrolyzed at. And they can be totally resilient to crushing load. So many people have heard of Julia Greer's work, where if this lattice you see on the bottom right was made of a ceramic, which it actually is, but it was on the macro scale, it would be pulverized if you try to crush it. And that's because brittle failure is driven by cracks in the material. But if you make the beams so small that they are smaller than the statistical likelihood of the size of the crack, then you don't have cracks, and they're actually remarkably resilient. This actually just shows crushing halfway, but you can crush the full way, and it still is resilient and works with very little damage. So you can make these things, if they're compliant single piece structures, very small, which increases computational density and facilitates much faster computational speed on smaller scales. Obviously not nearly as fast as electronics, but for these applications, it could be pretty effective and robust. So not surprisingly, many people in the Mechano-Intelligent system space has been naturally leaning toward things that deform elastically to perform their capabilities. There's a number of works that are purely mechanical, but also a hybrid between mechanical and electrical. And I wanted to talk about those systems first. This system here on the left is one I've done. And this brings us to take a little detour from the overarching story to explain about what we call mechanical neural networks. Okay, so mechanical neural networks are basically AI materials or metamaterials that can learn their properties and behaviors through increased exposure to unanticipated ambient loading conditions. And this is a macro scale planar version, not terribly practical, but was developed to test the concept and demonstrate learning for the first time. And this concept of mechanical neural networks is inspired by the mathematical diagram of artificial neural networks. It's basically a physical embodiment of them. So for artificial neural networks, you have numerical inputs multiplied by these scalar weights represented by these blue lines that are interconnected. The result of those multiplications is fed into these artificial neurons that are really just mathematical activation functions with biases. You go from layer to layer, and you tune these weights and biases to map known inputs to outputs, and that's how they learn. But imagine if, when I looked at this, I thought, well, it actually looks like a metamaterial in a way. What if we actually made those blue weights beams and the neurons nodes within a lattice, and instead of tuning the scalar weights to map known inputs to known outputs, we could tune using mechatronics, closed loop control. You could actively tune the stiffness or other properties of these beams to match known input forces and displacements to known output forces and displacements to learn the behaviors and properties of the material or the metamaterial. And so to show how this could work, imagine this 8-layer deep, 8 input node, 8 output node triangular lattice. It's grounded up on the top and the bottom. Imagine you wanted to learn a shape morphing behavior where when you push horizontally on the input nodes, these output nodes displace to certain target locations on this sinusoidal curve. Well, to do that, because each beam is outfitted with actuators and sensors, at any time it can sense the location of all the nodes, and you prescribe through closed loop control the stiffness. So from that, you can always know what forces are acting on this. So if there's these unanticipated forces driving it, whenever they drive it with the forces of the desired behavior, you can then measure the output displacements, subtract those displacements from the target locations, find an error, square it and average it, so find a mean squared error that you then optimize down to find a stiffness combination that works. And so this is how you'd find this axial stiffness combination within the beams, that when you load it, get this shape morphing behavior. So, but now say you want to learn a different behavior in addition to this. You want it to get smarter and continue to learn more and more behaviors. Well, say the next behavior you want it to learn is if you push up, it does this inverted sinusoidal shape. Well, you'd start with the combination of stiffnesses you found from the other behavior, because that's like its muscle memory in this intelligent system. And you'd start optimizing off of that, except you would find a mean squared error for this behavior and average it with the mean squared error of the other behavior and minimize that. And by so doing, you could find a combinations of stiffnesses that would simultaneously achieve both behavior. Notice these colors are all the same from one behavior to the next. And the neat thing is there's so many different combinations of stiffnesses that achieve these same two behaviors that you can actually learn more and more behaviors. And they don't just need to be shape morphing behaviors. They can be dynamic behaviors. They can be thermal behaviors. Really any mechanical behavior you like. This can autonomously learn on its own through control to exhibit these behaviors. So how do you actually embody this physically? Well, this is an active beam that we designed that worked very well. It uses precision flexures here to guide deformation along its axis, and uses a voice coil actuator, non-contact, so there's no rubbing, no friction. You'll see precision is critical to learning, as I'll demonstrate in the future here. We use strain gauges on the bases of the flexures to sense the displacement of this. And since we have actuators and sensors, we can now close the loop This is the controller we used. It's a Ph.D. Controller. And we use these 4 calibration plots that we measured from each individual beam to calibrate it. And we tuned it so that when we change this gain, Kp, it is the stiffness that it's going to exhibit. So you can see here, this instron for different gains, different Kps, we're achieving different stiffnesses or slopes of this force displacement curves. And you can see we can even achieve negative stiffness to assist, which is pretty cool. And so we took 21 of these beams, made them, calibrated them, put them in a planar lattice, triangular packaging. As you see here, we use these 4 other actuators to drive the input nodes in any direction using these decoupling flexures, and then cameras to validate the displacement of these output nodes. You can see there's these like white pinheads against the black. And those were just to validate, we can directly much faster measure the displacement of the output nodes using the strain gauges, but we wanted to validate that we're calculating those correctly with the cameras. So with this, that we wanted to demonstrate learning then, and we wanted to demonstrate the learning of 2 behaviors simultaneously, the 2 I showed before. First in red was you push with 1 Newton on these inputs, and this output needs to displace out and in 0.5 millimeters. And then the second behavior shown in green is when you push up, these do the opposite, 0.5 millimeters. And we used a genetic algorithm to optimize these to figure out what combination of stiffnesses to upload. And we try 1,000 stiffness combinations per generation using this. And we plot the one that got the lowest mean squared error, but we kind of cross-pollinate these 1,000 things to find the next generation of 1,000 things that would be better. And we follow this until we converge to a very small mean squared error. To see how this looks, this is the actual data from generation to generation of loading these 2 behaviors with particular stiffness combinations. And you can see they're crawling more and more toward their target values. It starts looking like a mess of spaghetti. So I'll start, here's the initial and the final. You can see it learned to approximate these shape morphing behaviors. And with more training and different approaches, we can get even closer. Okay, so it's a game of how quickly you can learn and how accurately you can learn with the lowest mean squared error. Okay, so once we had this system working, we wanted to test some hypotheses. We wanted to find what's the effect of learning with linear force displacement profiles versus nonlinear force displacement profiles. So we configured our controller so that with this function, we could plug in different force displacement profiles, linear and nonlinear. We had a hypothesis that nonlinear would work better because activation functions are nonlinear in artificial neural networks, and through reservoir computing, nonlinear is critical. But it turns out very ironically, or not expected, that linear is actually the better way to go. You can learn faster, converged sooner with a lower mean squared error with a linear force displacement profile. So we thought that was interesting. I also wanted to show you that was not our first prototype. That was our second one. The first prototype ended up being a failure, but like most failures, they're more useful than the successes because you learn a lot. And we learned a great deal from our first prototype. So I wanted to show you this real quick. We first made the flexures out of Teflon, 2 layers of Teflon that we sandwiched between voice coil actuators that probably could have had more clearance because they would rub and clank every now and again. We had Hall effect sensors and magnet stacks here to sense, and those had some crosstalk and some issues. But we put it in a lattice similar and tried to learn. And one thing we noticed is as the mean squared error was trying to converge, it would always jump up and it would never actually converge. So we could never actually fully learn. And we realized the enemy of all learning, very appropriately for this conference, ASP, is hysteresis. You need precision. If you have hysteresis and the system is always fundamentally changing from the material properties themselves, creep and stress relaxation, to bolts holding things together, slightly loosening, to any friction rubbing, bad tolerancing in the actuators, you're basically chasing a target that keeps moving, and so you never actually hit the target. And so we had to make that first prototype out of metal and make sure nothing's coming close to yielding and making sure nothing's touching. And it turns out precision is key to learning. But there were other hypotheses we wanted to test, other things we wanted to learn about learning that we really couldn't learn with just 21 beams in this planar lattice. And to make more beams, we'd have to, it'd be very expensive and time consuming and difficult. So we figured we would build a simulation tool to simulate this lattice or lattices made of beams from this lattice, so we could try much larger lattices and learn trends and like how many behaviors it could learn, that sort of thing. So we modeled these as just linear beams, shown here as blue. And using FEA, we calculated the passive off-axis display or stiffnesses that we use to inform the tool. And then through experimentation, we found the max and min stiffness between which we could program. This range, the max was 2.3 newtons per millimeter, and the minimum was -2 newtons per millimeter. And then using that, all that info, we informed the simulation tool, and that's how we were able to get these results I showed you earlier and do many other what-if scenarios. So the first what-if scenario we want to do is what's the effect of layers, like how deep these beams go back. So for an 8 input and 8 output node, we swept the layers of a triangular configuration like this. And we also want to find out how many behaviors can these things learn. So we generate random behaviors by having the force components on the inputs to be some random behavior between plus and -1 Newton in both components. And we paired them with the same displacement outputs with some value between plus and -0.5 millimeters. And we generated many, many behaviors and did a lot of averaging. This took a Hoffman supercomputer at UCLA like a year to generate all this data, to take the average. But you can see that the result is kind of as you'd expect. The more layers you get, the smaller the mean squared error, which means the more beams you have basically to learn with, and so you can learn with greater accuracy in general. But then, as we would expect, the more behaviors, the more random behaviors these things need to learn, the mean squared error goes up, which means it doesn't learn as accurately. So what that means is, it's very difficult to find a single combination of stiffnesses that can achieve more behaviors. So it's very understandable that you'd start losing some accuracy, but it still can learn quite a few behaviors. We also wanted to see what's the effect of beam configuration. So we tried square, triangle. In future studies, we're going to look at hexagonal packing and aperiodic packing, just random packing, to see what learns better. But these are results for square and triangular for different layers, 2, 4, and 8. And you can see mean squared error versus different number of behaviors. And of course, we see the same trend as the behavior number goes up, mean squared error gets worse, larger. But it's clear to see triangular packing is superior, and the more layers, as we found before, is going to learn more behaviors easier with better accuracy. And triangular packing is better because you can pack more beams in the same volume, but also because you can have information flowing in non-orthogonal directions, in all kind of more isotropic directions. Okay, so we also wanted to see what's the best optimization algorithm to use. So we took 6 very popular optimization algorithms: genetic algorithm, full pattern and partial pattern search, interior point, Nelder-Mead, and sequential quadratic approaches. And we took our mechanical neural network and we tested it for 2 sets of 2 random behaviors generated, as I described earlier, with 1 initial condition, and we just did 2 runs each. And you can see the results, the average of these results. This is the number of iterations and the mean squared error. And then we took the final mean squared and the final iterations and made this kind of cloud plot to start seeing a trend of which one's better. But of course, it's difficult to get a lot of data points in reality. We could do it much faster with the supercomputer. So we used our simulation also to back it up, to validate or verify this trend we're seeing. In this case, using our simulation, we did 2 sets, 2 random behaviors with 5 initial conditions, 10 runs. That's 250 runs each. And you can see for each algorithm, we plotted the average of all those, and these colored regions represent 1 standard deviation. You can see we plotted the average all together so you can compare. And then we plotted the final mean squared error versus the final iterations. This is really the key plot on the bottom right here. You can see that it's actually similar to the results we found experimentally. But the takeaway is, if you want really low mean squared error, By far the best way to get the most accurate learning is genetic algorithm, but it's also way slower than the others. So the best one really to use is Nelder-Mead here in purple. It achieves low enough mean squared errors to be accurate enough, but it can do it in much faster learning times. And we found Nelder-Mead is most resistant to system noise. So we would go with Nelder-Mead in the future with these. So that's all fine and good for testing planar macro scale lattices that were made of those beams I showed earlier. Those aren't very practical for applications. So the goal from the beginning was to make much smaller beams, like mesoscale or smaller, within 3D lattices, so you can actually have practical materials that can learn. And so this is a collaboration with Mike Cullinan, UT Austin, who's hosting this, where we designed this 3D material made of these unit cells that consist of 5 millimeter sized MEMS actuators, six of them surrounding individual IC chips. The entire lattice can be powered by putting a power and a ground on any of these actuators. They're all interconnected. And then the IC chip could send commands to each actuator, a voltage here and a ground here, to flow current through this double chevron actuator to drive it outward. And then you can pull it inward if you put a current through this actuator. And so we get bidirectional actuators that can do pretty large range and pretty large load capacity. And we use strain gauges, nano strain gauges on either side to sense the displacement. So now that we can sense displacement and drive them, we can do closed loop control to change their stiffness, damping, all sorts of properties to learn. We optimized the geometry of this and plotted the max and min extension and contraction, or the max extension and contraction before things would yield, buckle, or collide, or would overheat. We did the same thing for basically load capacity, maximum compressive stress, maximum tensile stress. Then we subtracted these, found the difference between them, and plotted them. So we found the range of programmable stress and the range of programmable strain. This is really the key plot where all the optimal designs lie on this curve. And you can see the trade-off. If you have basically a high load capacity, you have low range, and vice versa. We picked 4 designs that parallel the optimal design that were easy to fabricate. And this is where Mike's group fabricated these using 13 steps and tested them. As you increase the voltage, we got strains and displacements of the shuttle as we would expect, where device 4 got the largest, device 1 got the lowest, but that would have the highest load capacity. And then we closed the loop on these and showed that for different gains, you can tune the stiffness over large ranges. So just as expected, we can get large ranges and range of programmable stiffness. But the downside of thermal actuators is they have a slow response speed. So we wanted to characterize that. So it takes some time to heat things up and cool things down. So we put these, or Mike's team put these on a nano indenter holding at 1 micronewton. And we imposed different steps of stiffness on each beam. And we saw it took about 200 to 300 milliseconds to settle on and achieve the actual stiffness we wanted to program. So that characterizes its response, but good enough to learn a system for mechanical neural networks pretty quickly for many applications. Okay, and so this is actually, this is not a rendering. This is an actual video on a turn plate of a fabricated 3x3x3 system, and we're pursuing this together, still in an active collaboration. Okay, so back to kind of the main story here of I showed an example of a hybrid mechanical and electrical approach, but there are many groups out there that are doing purely mechanical. So the mechanical neural network had used electronics and a computer interacting with the mechanical system. These use no computer, no electronics, neither. They're just pure mechanical structures, and they can calculate and compute and do intelligent things. So the one that inspired us is this Jordan Rainey and Katia Bertoli's work at Harvard, where they basically built these AND gates, these logic gates, flexure-based logic gates that can compute. And the way they do them is they have this chain of springs with these bistable flexures that in their as fabricated state have no strain energy in them. But then you pop them up, pop them through to the right side here, to a higher energy state that's stable, and just like lifting up dominoes from on the table to up with more potential energy. And then you push them down, just like pushing down dominoes, and this soliton propagates through here. And if both propagate through, then it only pops through. Otherwise, it gets stuck. So that's how it's an AND gate. And so using this approach, I mean, you can do OR gates, you can do all sorts of gates. And through this, people have used applications, adapted the design, used applications to like lock or unlock doors and stuff. That the benefit to this approach is the soliton that passes through can pass through all these gates indefinitely. Just as many of these dominoes you can set up is how long the signal will propagate. The downside is that you can only push it from the high energy state to the low energy state. You can't do vice versa. And once you knock it down, it's a one-time use thing. To use it again, you have to set up every domino again. So it's not practical for more than one-time use application. So we set off with a collaboration with Lawrence Livermore. Bob Panis, many people know him in this. He was at Lawrence Livermore at the time, and we started this together and have a big group now with John Cortez and Hillary to fix this issue. And our design dealt with making a system like this that had a U-shaped strain energy curve. But if you then preload or compress this ground in, you turn the energy curve into a symmetric kind of W, where both states, a 0 state and a 1 state, are equal energy states. And this is important because if you put a bunch of these in series and connect springs in between them, and from your input to your output, you add these serpentine flexures that start stiff and then go to more and more compliant, what you can get is when you preload the ground, you get these symmetric W energy shapes, except from one to the next, they get a little bit smaller by some delta E. So that way you can switch from 0 to 1 state and back from 1 state to 0 state, and the soliton will always propagate from the highest energy to the lowest energy, from left to right, which means the system is now fully reversible without resetting anything, up. You can just use it over and over again and go from either 0 and 1 or 1 to 0, which makes this very practical and reusable. The downside of this is obviously eventually the energy runs out and you need to boost it. But we've worked on designs to do that, kind of boosters to get these things working. So here's something built at Lawrence Livermore where we use snap fits to preload the ground. Here we're demonstrating reversibility on the macro scale. You can see we go from 1 to 0 and the wave always propagates this way. It's also non-reciprocal, not surprisingly. You can't flow from the output up to the input. Here's a video showing in slow motion. At UCLA, we built our custom nanoscribe, basically, kind of a 2-photon stereolithography system. And we printed these at a small scale. This is approximately 200 microns across. And once you print them, you can see us preloading it with these snap fit features. Let me see if I can, well, we're almost done here. And then it'll show once it's all preloaded, you can see, here's the scale bar, you can see we can pop it through. And the wave, the soliton moves much faster in the small scale, you can imagine. And then you can see it goes back the other way. Okay, so we also built AND gates. Obviously, an AND gate, you need the 2 inputs being a state of 1 for the output to be 1, otherwise it stays at 0. So what we did is we took one of the inputs and we locked it in the 1 state. And we're trying to characterize here how the soliton can propagate through the gate. And you can see here we're demonstrating reversibility. It can go from 0 to 1 or 1 to 0, and the AND gate works great. Very soon you'll see here that it's also non-reciprocal. Okay, well, we just did that, but the next one you'll see it's non-reciprocal, meaning when you push the output, it doesn't work. It doesn't flow upstream. Okay, so at UCLA, we printed this very small, and you can see us preloading it. This is on our custom system. We made in with a mechanical kind of indenture thing. We're able to preload them and then actuate these. And you can see it follows the truth table of an AND gate, where only when both inputs are 1, the output turns to 1. And you can see the scale bar here, how tiny it is. So the vision is you could put all these memory bits and redirectors and AND gates and various gates together to do different truth tables and do some pretty complex computations. purely mechanically with no electrical power. We also have other gates, OR gates, NOT gates, NAND gates, NOR gates, basically a whole library of functionally complete gates that also are reversible and non-reciprocal. So we can do many other computations, not just AND gates that we've demonstrated. This is the work from Lawrence Livermore with transduction, different ways to drive the systems. So they came with liquid crystal elastomer that when they're exposed to acetone, they can expand. And when you take the acetone away, they'll contract. So you can use chemicals to trigger these things from the environment. Here's if you shine a laser on it, heats up, and these things can actuate. Inspired by that, this is a design also done at Lawrence Livermore where as you heat it up on a hot plate, you can pop these through. If you're okay using electronics, this is something we made at UCLA. We additively fabricated this, coated it in conductive metal, and then drove current through it to then heat it up and actuate. And here's us doing this, flowing current in different combinations to drive this AND gate so that when it pushes up here against these two electrodes, it could like turn on a light or something with a mechanical system. And this is what it looked like, super small, or in the SEM. And so, okay, so that's just some of the work we've been doing. We've been going pretty deep down that rabbit hole of using precision bistable flexure systems to achieve two different states, zeros and ones, and logic gates to compute things. But another way you can do mechanical computation is an analog approach where you use continuous deformation within compliant mechanisms to do some interesting computations. So I'll show you that. This is one example of a precision flexure system that it can add and subtract continuous deformation. So you'll see there's two inputs here and there's one output. It turns out the displacement, this continuous displacement of the output, equals to the sum of the displacements of the two inputs. That's how it adds and subtracts. So if you push it in, it's adding. If you pull it out, it's basically adding a negative number or subtracting. And you can see the trick of doing this as a compliant mechanism is when you push one, it's tough to have one mono structure kind of not have the other input also displace. So the trick is making them fully decoupled. So you can see this is a one-to-one displacement, but this other input's not moving at all. And then if we drive this is one-to-one displacement, but this one's not moving at all. If you do different combinations, they'll sum them together. So we built this on the macro scale first. We've also, with Lawrence Livermore, this is another collaboration with Lawrence Livermore. They've made one of our designs on the micro scale. And it works great on about 200 microns on that scale. Even though we're pushing here with our hands, you can see we put voice coils and laser sensors on this so that we could characterize this particular system. We drove it very slowly. This is a preliminary data. We hope to publish this soon. We have more advanced data here, but this gives you an idea. If you drive it slowly enough, then to be a perfect adder, you would lie on this target plane, this light gray plane. But the actual data we got is very close to being on this plane as an adder. But you can see with nonlinears of the flexure, parasitic errors, those sorts of things, it kind of peels off of the plane, but is a pretty acceptable adding mechanism. The interesting thing is because it's a compliant mechanism, it depends on the dynamics, right? So if you drive it really fast, you'll start inducing other mode shapes that make it so it doesn't do what it's intended to do. And so we locked one of the inputs and did a frequency sweep of the other input to get the Bode plots to carry this dynamics. We did it with the other input as well. Like I said, this is kind of old data, but to show you the idea. And the bottom line is, as long as you're driving the macro scale one at 3 hertz or less, it works great. Above that, it stops doing adding. This could be used as a plus if you cleverly designed a mechanism that at different speeds perform different computations. So that would be kind of interesting. Obviously, the bandwidth goes up as you shrink it down on a much smaller scale as well. So the pluses and minuses of a digital and an analog approach is that digital approaches where you're just snapping from a zero to a one state are much more accurate because if it say it doesn't quite go as far as it did the last time, it doesn't matter as long as it's popped through to the one state. And then when it's in that state, it's pretty susceptible to vibrations and dynamics because it's tough to knock them out of their stable state. So it's very accurate. It's not susceptible to vibrations because they're compliant. They're repeatable. They're scalable. The downside is they're relatively slow. So the macro scale, that soliton that propagates through the system, goes just a little faster than the fastest human can run, which is pretty slow. And of course, it would go much faster if you shrink it down to its intended scale of the micron scale. But it's still pretty slow. And if you want to do complex computations, say you wanted to do Pythagorean's theorem, or do some kind of complex function, you'd need quite a few logic gates, and you need boosters and all sorts of things. So it starts getting pretty complicated. Whereas the analog approach, it's much faster. It's limited by everything kind of continuously deforms together. It's limited by the speed of sound in the material, which is much faster than the soliton that propagates through these bistable gates. And instead of needing lots of tiny little building blocks stitched together, you can just use one little module that performs whatever you want: adding, multiplication, sine, cosine, any function you could write on paper. You can make a mechanical version that just does it in one building block. And so and it's very repeatable. You can get really high resolutions as long as nothing yields, and we follow the rules of precision. It's scalable. But the downside is relatively inaccurate. It's tough to get it to match and stay on for large ranges, stay exactly doing the computation you want. But through clever design, you can mitigate that, and you can calibrate and get it to be pretty good. But it is susceptible to vibrations. Of course, the smaller you shrink it, make it small, the less that matters. Or it would only be affected at higher frequencies. But you could either leverage that for your good, or just be aware of it and design so you're not in environments that are above the bandwidth, right? So interesting, and it would be interesting to combine these. There's actually work in doing digital to analog converters in the purely mechanical realm. So with that, these are the three kind of areas: mechanical neural networks, digital approach, analog approach to doing intelligent things like computing, sensing, control, and learning. One cool idea would be to replace all the computer electronic side of the mechanical neural network with a mechanical computer that's doing the optimization and that sort of thing. That's many years down the line, but we need to have a purely mechanical neural network that didn't use any power or electricity and just relied entirely on mechanical means. And so with that, I'd like to acknowledge my team at UCLA and for having their hand in this. I should have been acknowledging Mike on this. I'm just realizing, Mike, I acknowledged you earlier. UT Awesome, the work with the the MEMS mechanical neural network. But I'm acknowledging Lawrence Livermore here with their contributions to the digital mechanical logic work that we've been collaborating on for some time. And so with that, I'll end here.
Great, John. Thank you so much. I think we'll open up for questions. People can either unmute, or they can put the question in the chat if they prefer. Um,
Okay, I have a
yeah,
question.
there we go.
Yeah.
Yeah, cool.
So in you talked about this approach to mechanical systems with flexures reduces the wear and the clearance and susceptibilities associated with sliding contact. Uh, is fatigue life a consideration here, and is that mainly addressed through material choice, or is there, I mean, if we're thinking about, millions even billions of operations. Does fatigue enter into this?
Yeah, so yes, great question. If you're doing something, if I'm trying to do like what Charles Babbage did, made a flexure version of a computer where you're going to get millions and millions of things throughout the use, fatigue would certainly come into it. But it could be addressed with material and topology, with hard stops and stuff to make sure the stress never rises above the fatigue limit of the material. Also, when you shrink flexures down, some of those issues are mitigated a bit as well. But we're actually targeting, since that's probably 20 years away from being able to do like a full computer kind of thing. We're actually targeting with these mechanical logic things and analog things, more simple stimuli responsive sensors sometimes are only used just a couple times. So fatigue isn't that big an issue. So it depends on the application, but for the applications where it matters, and you need to address it. So, but it's addressable. That's the important thing.
Right.
Great question.
We had a question in the chat. How does this scale to high volume manufacturing?
So it depends on which of the applications. Let's for scalability is tricky right now if you're trying to make these things at tiny scales. That's definitely one of the challenges. Fortunately, the target applications we're pursuing are very, very, very small devices. You could put markers on things like one application that's proposed. So someone recently has put kind of a marker on some device you want to ship, and it can track if during transit the device exceeded a temperature or got slammed, someone dropped it, some acceleration, it experiences beyond some acceptable G-force, or it went through some pressures that, or it was exposed to chemicals you didn't want to expose to. These things can track it and trigger and do logic and compute with very small little computers. So the applications right now don't require it to be scaled, but yes, scaling would be a challenge that many people are working on, and it's not insurmountable, but needs more research.
And then we got another question. What are some of the next frontiers extending this work in your view?
So each of the three categories I presented on have lots of future work we're planning on doing. For mechanical neural networks, you and I, Mike, we're trying to get different kinds of smaller mechanical neural networks, 3D, that respond quicker, larger range of programmability, and demonstrate them on small scales. So the dream would be to not use actually MEMS to make mechanical neural networks, but make them really small with multi-material 2-photon and print them with conductive and non-conductive materials and insert the IC chips during the printing process, and then demonstrate those on tiny, tiny scales. So there's a lot of future directions and studies that need to be done with mechanical neural networks. So it's kind of launched a whole field in that area. And then the other two areas, mechanical digital logic, there's all sorts of things we need to do. If we're going to pursue the vision of like a full-on computer, we need to do flexure-based counters, better memory storage devices, boosters, amplifiers, that sort of thing. The issue of scalability, you saw a lot of the designs are planar. We could do a lot of logic in a much more compact space with 3D designs. So there's lots of different areas. Materials need to be researched to get to make them, be able to additively fabricate them, but have them be resistant to harsh environments, those sorts of things, and similar things with analog. But with analog, there's also lots of research with boosters. Since they're compliant mechanisms, if you chained a bunch together, say a bunch of adding, multiplication gates and those sorts of things together, the analog, at some point, the energy that you input by deforming gets absorbed with all the strain energy of all the other deformations, so the output can't even deform. So it's obviously not going to be able to compute. So we're going to attach negative stiffness flexures onto these things to cancel the positive stiffness flexures and infuse more energy to kind of boost these signals, and then get systems to interact with digital and analog to do certain specific applications, as well as explore different stimuli responsive materials to kind of drive these things and pursue some of our exciting applications that some customers are pulling for and that sort of thing. So there's, I mean, this could go in lots of directions, but that is our three-prong effort right now. So in those three areas.
If you're gonna build like a um, mechanical computer, do you see kind of the digital or the analog as kind of the more scalable pathway to doing that?
I think some of it would be analog and some of it would be digital. The
Mhm.
parts that make sense. That I'd like to kind of start a center about this Mechano-Intelligent thing and get a whole crew of all the people working on it to kind of pursue that kind of vision. But there's a lot lower hanging fruit than a computer. I'm not sure
Sure.
we'll ever go the direction of having a full compliant mechanism computer. That would be awesome. But there's a lot lower hanging fruit applications that are arising that are interesting. We're pursuing first.
So the question was, what is the low-hanging fruit out?
Yeah. So I talked about little sensors that are stimuli responsive that little markers you could put on things for anti-tampering things that you could tell if in transit some machine you ordered had experienced G forces or temperatures or chemicals that were unacceptable. This device could tell you and calculate that. There's other things for space, like say you're launching something in space and you want all your electronics, your power systems turned off till you reach a certain environment. Say you reach a certain pressure or temperature outside or whatever, and it then mechanically triggers things power free to wake up your electronics. There's other things where you could have sensors that have multi inputs. Like imagine you took a phase diagram for a material and you encoded that information in the chart in some analog machine, little structure where there's an actuator that does pressure and an actuator that does temperature. And depending on the combination of that pressure and temperature, you could have the output flick a switch that says, okay, now this material has turned solid or this material has turned into a gas without actually having the material there to turn to solid or gas. You could like encode things like that. So there's lots of sensors is the first low hanging fruit for these sorts of things. And then closed loop control, you could take the output of these and loop it around to the input and put in plants. So, the first, steamboats have that the governor, spin around and open the slot to get more oxygen to feed the fire and stuff. So they could regulate the steam engines with this. This is purely mechanical. It's like a closed loop control system. There's things like that you can do, like immediate, like reflex response things. In fact, DARPA just put out a call to do this, where you have mechanical intelligence that without power, without anything, untethered robots can react kind of reflexively to things with kind of closed loop control, mechanical systems and sensors without power and potentially in harsh environments. So that's kind of the next thing. And then the next thing would be, full on computers and that sort of thing, if there's interest for that.
How does this fit in with like the concept of like reservoir computing that people have gotten excited
So
about
this it's
recently?
pretty different. It's pretty different. With theirs they use the nonlinearity of
Yeah.
systems kind of then interact with artificial neural networks that like tune weights and stuff to get things. But this is just taking the neural network thing. This takes it's basically a physical embodiment of an artificial neural network chart where you're tuning the beams to like you tune the scalar weights to get the properties. And so, and it doesn't behave anything like it doesn't really get any inspiration or get any behavior from reservoir computing the way that works. In fact, like I showed, linearity is actually important to learning in mechanical neural networks, whereas it's the nonlinear that's important to the computation of reservoir computing kind of approach. So it's very different, but obviously related. It's in the same field, and I'm sure it
Mhm.
could be inspired and integrated in to get more interesting computational systems. We're also interested, by the way, in looking at using mechanical structures that are embodiments for quantum computing inspiration things. There could be some really neat things to be learned to embody quantum computing in the mechanical realm, and combining all these to do other cool applications. So, yeah.
I think we have one last question here. My understanding is that modern neural networks are usually fully connected. Your last example seems like a node might be connected only to only a few other nodes. Do you have a route towards higher connectivity for those lattices network types?
So it's actually interesting. Can you still see my screen?
Yeah, we can see your
Yeah. So it's interesting with um, with if this is just a mathematical diagram, you can connect any way you want. It doesn't matter if these blue lines overlap. It's just a diagram showing connectivity. With mechanical neural networks, obviously the beams can't pass through other beams, so they have to be geometrically feasible. So you can't get as much connectivity, but you can get enough to learn, as we've demonstrated. But we're really interested in taking. We've got a grant review right now of taking mechanical neural networks into the 3D realm. And if you do 3D mechanical neural networks, you could imagine you could get a lot more connectivity because you have spatial dimensions instead of just planar. So you could get rhombic dodecahedrons with 12 beams coming out of each node, and to get more connectivity. And we hypothesize, obviously, that will learn better. We think, that we might be surprised. That might increase the complexity, so it screws things up. But with more connectivity, we expect we should be able to learn with greater accuracy. So I don't know if that answers the question.
uh does anybody else have any other questions for today? I think we have like a minute left or so. Um, yeah, perhaps via kind of connecting rather than Z. Yeah, I think that's
Yeah.
kind of what John was thinking about. Um,
Right.
but I guess I think we're about out of time, so I want to thank John again for kind of giving this presentation. I think we're recording it, so we'll figure out a way to post it on some place that's accessible through the ASP website in the near future here, along with the rest of the seminars in the series. But I want to thank John again for kind of coming in and talking. And we should have our next seminar in about a month. And so look out for kind of the announcement on that upcoming seminar in August.
Awesome. Thanks, guys, for the opportunity.
Thank you. Thank you for presenting. Really appreciate it.
Yeah. All right. Have a good one. Thanks, guys.
Mhm.